In this video, we're going to go through section 2.4 of the calculus textbook. The section talks about the precise definition of the limit. Okay, so up to this point in these first three sections of chapter 2, we've been talking about the meaning of limits abstractly, right? In section 2.2, which was the section in which the idea of the limit was introduced, we developed a very strong intuition for what limits are and what they mean. But we never made any official formal statements about what exactly the definition of a limit is, right? If we come back to the start of section 2.2, you see how this definition of the limit here is titled the intuitive definition of a limit. Again, all we did in this section was develop a strong intuition for what limits are and what they mean. Now, in section 2.3, we learned some mechanical laws that would allow us to evaluate limits without having to resort to non-bulletproof methods like guessing a limit with a calculator or doing a limit purely graphically, right? So these limit laws shown here. And we also developed in this section some additional laws using these limit laws as a starting point. So with what we learned in this section, we could be given an actual limit problem like shown here. The limit as the independent variable approaches some value of a function, an expression of that independent variable is equal to what? And we could solve a limit like this, so get the exact value L of what a limit like this was equal to. And this limit here is actually equal to 2/3. Okay, and so again, before this section, so with what we learned in section 2.2, the only way we could solve this, or even like think about solving this, was to use our calculator and plug in values of u into the function that were very close to 2 on both sides of 2, and then just examine what the function is doing. But we learned how this isn't a bulletproof method because our calculator can only handle so many digits. Now, also, we could potentially think about analyzing the graph of this function, analyzing a graph of this function. So using a graphing software like Desmos, for example, we could graph this and then just do a graphical limit problem, right? We had a whole video on solving graphical limits. And that would probably work in most circumstances, but still, as we talked about, that method as well wouldn't be completely bulletproof in all scenarios. Okay, but even though we could get the exact value of this limit using the limit laws and the other laws that were developed in this section. So again, after going through section 2.3, we could get the exact value of this limit. This limit is exactly equal to 2/3. We still have no idea where these laws came from. The calculus textbook just gave us these laws and told us to trust that they were correct. Okay, so how are these laws proven then? And really, when asking the question, how are these laws proven, you first need to ask, what is the exact definition of the limit, right? If you don't know what the exact official definition of the limit is, then you can't prove laws like this that involve limits, right? And so, okay, the question then that we're asking is, so this limit here, the limit as u approaches 2 of the principal square root of 4u plus 1 minus 3, all of that over u minus 2, is equal to, we know, is equal to 2/3. But, okay, what does this mean, though? What is the exact official meaning of this? What does the subject of mathematics say is the official meaning of a limit? And then how would we prove that, based on the official definition of the limit, that according to that definition, 2/3 is the value of this limit? Well, okay, fortunately, if you've been following along with the videos as we've gone through the first three sections of this chapter, you already know what the precise definition of the limit is. We've been talking about it over and over again. The only thing that you don't know is how to state this definition mathematically, or how to prove that a limit like this, so prove that 2/3 is the true precise limit of this function mathematically. But again, as far as what the precise definition of the limit is, conceptually, we've already been talking about this over and over again prior to this video. The precise definition of the limit is the whole infinitely powerful calculator thought exercise that I've been periodically mentioning. That's the precise definition of the limit. It's the idea that, so for this limit here, this limit is equal to 2/3, because we could imagine a scenario where we had an infinitely powerful calculator that could handle quintillions of decimal points. Okay, and so coming back to the intuitive definition of the limit, so the limit as x approaches a of some function f of x, it exists and is equal to L, means that we can make the values of the function, the outputs of the function, arbitrarily close to L as we like, by restricting x to be sufficiently close to the input on either side of the input. So yeah, this is not a one-sided limit, so we're thinking about we're getting us close to the input as we like on either side of the input, but not equal to the input. And in the process, we can get as close to L as we like. However close to L we want to get, we can do that by just getting as close to x on either side of A as we need to get. So for this limit here, the idea is, using our infinitely powerful calculator, we could plug in u is equal to 1.999 1,000 nines and see what the function is doing. Then plug in 1.999 a million nines and see what the function is doing. And then again, since this is not a one-sided limit, we would do the same thing coming from the other side of 2. So plug in 2.000 1,000 zeros 1 into the function. Then plug in 2.000 a million zeros 1 into the function and see what the function is doing. But we could just keep going and going and going with our infinitely powerful calculator and just examining what the function is doing as we get closer and closer and closer to 2 coming from both sides. And if it's clear that as the input gets closer and closer to 2 coming from both sides, the function also at the same time is getting closer and closer to some value L, then we say that, okay, in that case, the limit is equal to L, right? That's the intuitive definition of the limit. All right, but now the other parts of this definition, so let's see. The idea of an open interval that contains A. What does open interval mean? Why an open interval? Well, because when going through this hypothetical infinite calculator exercise, where exactly we start in the process of approaching A from either side doesn't matter, right? Like it doesn't matter if to approach 2 from below, if we start at 1, or if we start at 1.5, or to approach 2 from above, if we start at 2.5 or 2.3, that means nothing. It's all about when you're getting infinitely closer and closer is what it's all about. So that's why they specify it's an open interval. It's not closed. Where you start doesn't mean anything. Okay. Also, as we've talked about, a very important part of the definition of the limit is what the function is doing at the limit value itself means absolutely nothing, has absolutely nothing to do with the definition of the limit whatsoever. So like f of a, as far as what the definition of the limit, yes, we're going to see how, and actually we've already seen in some sense that you can evaluate a limit depending on if it's certain types of limits by plugging in a into the function. So evaluating f of a, that's true. But that's just a trick that we use to evaluate certain limits. It just works out that the function evaluated at the limit value happens to be the limit, what the limit is equal to. However, as far as what the definition of the limit is, the precise meaning of the limit, what the function is doing at the limit point itself, at A, it has absolutely nothing whatsoever to do with the meaning of the limit. Okay, and then also, what about when x is near the number a. What does near mean? Okay, all near a means is that the whole hypothetical infinitely powerful calculator idea needs to kick in at some point around a. Now, what point that is doesn't matter as long as it does kick in at some point. So what I mean is maybe this limit here, just hypothetically, maybe, if we plugged in 1.999 a million nines into the function, into our huge calculator, maybe the output is doing something crazy. We see the output is doing something crazy. It's equal to like negative 1,032. Maybe it is. And same idea from the other side. If we plugged in 2.000 a million zeros 1, looked at the output, it's doing something crazy. Then we plugged in 1.999 5 million nines and looked at the output, and it's at positive 1,000 something or positive 5,320. So it's all over the place. But we're very close to 2 on both sides, right? And the function is just acting crazy. But as long as at some point, so if we at some point, let's say we plugged in 1.999 a trillion nines into the function, then we saw there was some value that was output. Let's just say in this case it's something like it's close to 2/3, but it could be whatever. And then we went to the other side, since this is not a one-sided limit, and plugged in 2.000 a trillion zeros 1, and we were seeing, okay, we're also getting a similar value on the other side, and then we kept going. So we plugged in 1.999 a quintillion nines and saw that, okay, we were getting a little bit closer to what we saw at 1.999 a trillion nines, and did the same thing from the other side, and then just kept going and going and going. And as we, 100 quintillion, 500 quintillion, and we just kept going, and we saw, okay, we were approaching something coming from both sides, the same output, then that is the limit. Then that limit exists, and whatever we're approaching is the limit. We would officially say that the limit is equal to 2/3. But even then, though, there's still an issue there, though, because you could say, well, okay, well, how long do we need to do this? What if we went past 500 quintillion and quintillion nines, and all of a sudden the function started doing something crazy again? Well, then in that case, the limit wouldn't exist. The idea is for the limit to exist, we could the infinitely powerful calculator concept would kick in, and then no matter how many decimal points we used, no matter how many decimal points close we were to the limit value on either side, we would always be approaching the limit value coming from either side. That's the true definition of the limit. But how do we prove that? How can we prove this mathematically? That this whole intuitive definition is in fact the case here. That this limit is truly equal to 2/3. Well, okay. Well, it starts out in this section pretty much stating the motivation for the need for a precise definition of the limit, which is everything I've just been talking about. So here, we could plug in 0 into this function, and we would get the limit value, but we haven't made any official statements yet about if direct plug-in is applicable for a cosine function. And so if we come back to this problem, this was in section 2, what they're showing is that, so if you thought about using a calculator to try and guess the value of this limit, so they're plugging in x values closer and closer and closer to 0 coming from above 0. Well, okay, you might guess that this limit is approaching 0, right? However, what they're showing is that if you decided to keep going, so x is smaller and smaller and smaller, well, then you would see that the limit is actually, it is approaching, it's not approaching 0, it's approaching something that's close to 0. It's approaching 1 over 10,000. And so what they're illustrating here is, how do you know where to stop with a calculator if you're trying to guess a limit with a calculator? How close to A do you need to plug in before you can state what the limit is, right? Like, even if we were able to plug in a million decimal places, 0.000 a million zeros 1, minus 0.000 a million zeros 1 and then see what the output is doing. How do you know that that's enough? How do you know where to stop? Okay, and this limit here, we were able to guess correctly using the calculator plug-in method, but still, like it's saying, how can we prove conclusively that these limits are what's shown here, right? We must make the definition of a limit precise. So, okay. It says to motivate the precise definition of a limit, let's consider this function f of x, which is defined to be, this is equal to 2x minus 1 if x is not equal to 3, but if x is equal to 3, this is equal to 6. And it says that intuitively, it is clear that when x is close to 3, but x is not equal to 3, then f of x is close to 5, and so the limit as x approaches 3 of f of x is equal to 5. Okay, but now let's remind ourselves, why is this intuitively clear? Well, because we understand the function 2x minus 1, right? We know what this is, that this is the equation of a line. Now, this entire function f of x isn't exactly a function for a line because we have this exception here that when x is equal to 3, this function is equal to 6, which is off the line 2x minus 1. However, because we know when it comes to the meaning of the limit, what's happening at the limit value means absolutely nothing. And then with that, according to the definition of this function, at absolutely every possible real number other than when x is equal to 3, this function corresponds to this line 2x minus 1, then really to think about this limit, we're just thinking about the line 2x minus 1 then, right? And so then if we think about a line, as we know, a line is just a continuous, unbroken curve that extends infinitely from x is equal to minus infinity to infinity, then intuitively we would say that the limit as x approaches 3 of this function is just whatever the line 2x minus 1 itself is equal to when x is equal to 3, which is 5. And actually, based on the limit laws we learned in the previous section, we could officially state that this limit is equal to 5, right? Because we could do a direct plug-in. This is a polynomial, and we just do a direct plug-in here. Okay, but now, how can we analyze this from the perspective of the intuitive definition of the limit, though? So it says, to obtain more detailed information about how f of x varies when x is close to 3, we ask the following question. How close to 3 does x have to be so that f of x differs from 5 by less than 0.1, right? So to try and analyze this limit here, the limit as x approaches 3 of this function is equal to 5, the meaning of this limit, from the intuitive definition of the limit standpoint, we want to try and analyze how f of x varies when x is close to 3. And so we do this by thinking about the question, how close to 3 does x have to be so that f of x, the output, differs from 5 by less than 0.1? Okay, so what we do is we say that, okay, the distance that x is from 3 is based on the absolute value of x minus 3, right? The absolute value accounts for the fact that we could be on either side of 3, okay? And then the distance that the function is from 5, and similarly, is just the absolute value of f of x minus 5. So, okay, our problem is to find a number delta such that, so the requirement is that we want to have the absolute value of f of x minus 5 be less than 0.1. That's what the question stated. We want to be within the output f of x to be within 0.1 of 5, the limit value. Okay, but the question is then, what are all of the x values so we could plug in any x values within some interval that would satisfy this inequality, and those x values are based on what? Well, those are based on when x is within delta from 3 on either side of 3. But we're not considering x what happens when x is equal to 3. Any other x value other than 3 The idea is if x is some positive or negative distance away from 3, other than it's exactly equal to 3, with that distance from 3 being some positive value delta, as long as we plug in an x value that's delta away from 3 into the function and then subtract that output of the function from 5, then the magnitude of that distance is always, under all circumstances, going to be less than 0.1. Okay, so let's continue to analyze this. So, okay, what they do next is they say that we can restate this here without having to say x is not equal to 3 by just stating that the absolute value of x minus 3 is less than delta and greater than 0. So now, in this case, x can't be equal to 3, because if it was, then it would be equal to 0. Then the absolute value of x minus 3 would be equal to 0. Okay, so now we've restated our problem with these two inequalities here. The absolute value of f of x minus 5 is always less than 0.1 if you're restricting the x values that you're inputting into f of x based on this inequality here, this restriction, that this magnitude here, right, the absolute value of x minus 3, this positive number, is never equal to 0, and it's always less than delta. So what does delta need to be? Okay, so what they do is they say that, okay, notice that if we said that delta was equal to 0.05, and we don't know why they're saying that at the moment, so let's just say delta was equal to 0.05, to where 0.05 is 0.1 divided by 2. Let's just say that. So if we take 0.1 and divide it by 2, that's delta. So you take this inequality and you replace delta with 0.1 divided by 2 is 0.05. So the absolute value of x minus 3 is greater than 0 and less than 0.05. Okay. Now, what they do next is they just take this inequality here for the output, and, well, actually, they just take the absolute value of f of x minus 5 first, and they say, okay, let's plug in the 2x minus 1 for f of x, which is what the function equals to when x is not equal to 3, which is all we care about. So they plug in the 2x minus 1 for f of x. They simplify this to get the absolute value of 2x minus 6. And now we can factor out a 2 from the absolute value, right? And we get that the absolute value of f of x minus 5, when x is not equal to 3, is equal to this. Okay, but now what we notice here is that we have the absolute value of x minus 3 here, which corresponds to our input restriction. What we have is 2 times the absolute value of x minus 3. So if we can multiply this entire inequality by 2, and you would get 0 is less than right? And so there's 2 times the absolute value of x minus 3. So we can say that this is less than 2 times the delta, 2 times 0.05, which is 0.1. So we took the absolute value of f of x minus 5 and we converted it into this. So these are equal. These two are equal. Now, but then we said that, okay, this is less than 0.1. So what we just proved is that if we chose delta to be equal to 0.05, then we just proved that this is the case. If delta is, with this restriction here, this inequality, if delta is 0.05, then this. So there you go. We just answered the question. Delta then is 0.05, right? So that they make the statement here. Delta is 0.05. Now, one thing I want to point out here is that note how we truly did just prove that. So, okay, if we solved this absolute value inequality, then you would get that x is greater than 3.05 or less than 3.05 and greater than 2.95, right? That's what you get when you solve this absolute value inequality. What we just proved is that you could plug in absolutely any value of x you could possibly imagine, right? There's an infinite number of values between 2.95 and 3.05. You could plug in any of those values you want into the function, into this function, as long as x isn't equal to 3, into this function. And no matter what, if you took the output of the function and subtracted it from 5, no matter what, the absolute value of that is going to be less than 0.1. It's kind of weird to think about, but I mean, literally, any value of x between 2.95 and 3.05, there's an infinite number of values of x, right, that you could choose. I'll say it again. If you chose any one of those values and you plugged that value into this function, as long as x isn't equal to 3, then you subtracted what you got from 5 and took the absolute value, what you get, the result will always be less than 0.1, no matter what. And you might say, well, how do we know that for sure? Well, it's all algebra, right? It's like in algebra, when we're solving equations or inequalities, you might solve an inequality and get the answer is x is less than 5. Well, we prove in algebra, we're talking about like the entire real number line. There's an infinite number of values on the real number line. There's an infinite number of values between just 1 and 2 on the number line. So if you properly solve an inequality and you get that x is less than 5, then you have stated, by the rules of algebra, the laws of algebra, you have stated that if you plugged in absolutely any value on the real number line that is less than 5 into the inequality will be satisfied. And there's like an infinite number of values, right? You could plug in x is equal to negative 100 quintillion, and it's going to satisfy the inequality, right? We started here. We formulated this question. We were given this question, and we just wrote out this question with inequalities. It was completely valid here. This is just, all we did here was, well, really, we updated it here. This is where we officially, all we did was just state this question with inequalities. That's all we did here. This was completely valid, right? So we want to answer this question. We restated this question with inequalities. Then from there, we used valid algebraic techniques to prove the final statement here, to prove that the delta we were asking about is equal to 0.05. You see? So thus, an answer to the problem is given by delta is equal to 0.05. That is, if x is within a distance of 0.05 from 3, then f of x will be within a distance of 0.1 from 5. And there you go. Okay, now what it talks about next is that if you think about it, we could have changed this question here. We could have specified a smaller number. So you could have specified that the output, the distance from the f of x from 5 needs to be within 0.01. And that wouldn't have been an issue at all. We would have gone through the exact same procedure and gotten this new answer here, that delta needs to be 0.005, which is just 0.01 divided by 2. And similarly, we could have specified that the distance of the output from 5 needs to be 0.001. And then delta is going to be 0.001 divided by 2. And what they're showing here is important because the idea is we could have specified what they're calling, so the distance of f of x from 5, the absolute value, is we could have stated any number epsilon that we want. That this, if we come back here, this value, this original question, how close to 3 does x have to be so that f of x differs from 5 by less than 0.1? We could have just stated this as epsilon. And then what we're trying to do is solve for delta, right? And all it would be is, what we just saw is that the answer is going to be that delta is epsilon divided by 2. But this is really important because what is epsilon? What is in algebra, what is a variable? What does a variable represent? Assuming we're not thinking about imaginary numbers, if you just state a variable, just list a variable like this with no restrictions, just here's a variable. What does this mean? This is a placeholder for any real number you want. Any real number. So this is really powerful because since this can be any real number, then we've just proven then that this limit is, according to our intuitive definition of the limit, the infinitely powerful calculator, we have proven that this limit here, the limit as x approaches 3 of f of x is equal to 5, we've proven this limit because we've shown definitively that we can pick any value of epsilon that we want, any real number that we want. So we can say E needs to be 0.000 a quintillion zeros 1. That's how close f of x needs to be to 5. Then, okay, but now we have to then answer the question then, what is the corresponding delta then? The interval around that the input is around 3 that corresponds to this epsilon value. Well, it's just going to be take that epsilon divided by 2. But we could do this for, make E 500 or 0.000 500 quintillion zeros 1. We could go as infinitely small as we want. And no matter how small we go, we're still going to be coming from both sides of 3. If the input is on either side of 3, we're going to be sandwiching or constraining the function at this value 5. If we're just insanely, infinitely close to the input x of 3, insanely, infinitely close on either side, then on either side, we're going to be insanely, infinitely close to the output being 5. You see? You see how we just proved this limit as x approaches 3 of f of x is equal to 5? Okay, so what they do next is they just try and illustrate what we proved graphically. And really what they're talking about for these next couple of pages is trying to make sure it's clear what exactly the precise definition of the limit means mathematically. And this is a little bit confusing at first, especially when you consider that, so for the limit we just did, the limit value was being sandwiched from above and below. But as we've seen, this isn't always going to be the case. We've seen limits like, for example, this limit here, the limit as x approaches 0 of sine of x over x is equal to 1. The graph looks like this. So here's 1, and the function approaches 1 from both sides of 0 from below. It doesn't sandwich 1 coming from either side. Okay, but this is also a little bit confusing because what I found when I first learned the precise definition of the limit is it's easy to get really focused on epsilon and delta and forget about the main point of what we're doing, in that the limit point A and the limit value L were intimately involved in the entire limit proof that we just did. So, but okay, let's read the precise definition of the limit first. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. All right, so we have a function and some input value a. And we're saying that the function is defined on some open interval around a, so on both sides of a. But what the function does at a itself doesn't matter. All right, but you can see how they aren't making any statement about exactly how the function exists around a, right? It's just that the function does exist to some extent in some interval on both sides of a, except what the function does at a itself doesn't matter. Okay, then we say that the limit as x approaches a of the function f of x is equal to L. So, okay, yeah, we aren't talking about a limit at infinity here. So as x approaches infinity, we haven't gotten to limits at infinity yet. So a, the limit point, is going to be a single finite number, and then also the limit is going to be equal to some single finite number L. So like we aren't talking about infinite limits at the moment, right, where this would be equal to infinity. We'll talk about infinite limits towards the end of the video. Okay, now, and also note that we aren't talking about a one-sided limit here either. This is as x approaches a in general. So the limit as x approaches a of some function f of x is equal to L if for every number epsilon is greater than 0, there is a number delta that's greater than 0, such that if the absolute value of x minus the limit point a is between delta and 0, then with this restriction, the absolute value of f of x minus L, the limit value L, is less than epsilon. If this is true, what's stated here is true, if this is true, This part is the definition of the limit. Okay, so let's break this down, the definition of the limit portion. First of all, note how epsilon and delta are just general variables with no restrictions. This means that epsilon and delta can be absolutely any real number you want, which is the key to the whole infinitely powerful calculator idea. Well, actually, no, I take that back. No, they can be any positive real number you want. So yeah, it's any epsilon that's greater than 0 or delta that's greater than 0. So any positive real number you want, as long as it's greater than 0. So it could be, epsilon could be 0.000 a trillion zeros 1. That's fine, as long as it's greater than 0. Same idea with delta. Okay, so first of all, what is delta? Okay, delta is absolutely any positive real number on the number line, no matter how small it is, that represents the largest distance some random x value is from the limit point A. So with a general two-sided limit, delta is just defining some set of x values that you can pick from, some set of x values around the limit point A that you can pick from. It's restricting the x values that you're going to be picking from in regards to this whole definition of the limit here. We're putting a restriction on the x values. Delta is saying that, so when we come to this second part here, the second part of the definition of the limit, delta is saying that you can pick any x value you want on either side of A as long as you aren't delta away from A. And at the same time, as long as that x value isn't equal to A itself. Otherwise, the absolute value of x minus A would be 0. Okay, but again, it's important to note how there are no restrictions on what number delta is, other than it has to be greater than 0. That's extremely important here, because then with that, then delta is just a variable in the sense that delta could be 0.0000, a quintillion zeros, 1 if you want, right? Okay, now then what's this second part? Okay, the L is very important in this second part, the limit value itself, what the limit is equal to. The A in the first part, the limit point A, it is important, but the only thing is, for any function, no matter what the function is, so whether or not a limit exists or not, we could make a restriction like this, right? There's nothing special about a restriction like this. All we've done here is just map off a region of x values on the number line, right? So like all functions, no matter what the function is, have inputs. And with this first part here, all we're saying is that, so like, look, say we're restricting the inputs into this f of x for the limit, this limit function. Let's say we're restricting the inputs to this interval here. That's all we're saying with this first part, but also not including x being equal to A itself. So like we could make a statement like this for any function, no matter what the function is. So we really haven't done anything special here, okay? But the key is for the limit to exist and be equal to some finite single value L, with this first restriction in place, this inequality also needs to hold at the same time. If that happens, then this limit is true. This statement is true. Okay, and so what this means is that for this limit as x approaches A of f of x to be equal to L, for this to be true, then with this restriction on the potential input values given by delta, then if you take any of those x values, absolutely any of those x values within this interval that you want, and plug them in to this inequality, so into f of x here, then in all cases, this inequality will be satisfied for some other random single finite value epsilon. Okay, so, but what is this inequality exactly? Okay, so all of this is a little bit confusing at first. Okay, so first of all, note that, yes, while delta and epsilon are variables that represent any real number that's greater than 0, okay, they aren't variables at all when you're actually going through this whole process. Like this is saying that you could pick a single finite delta value first. Say you pick delta to be equal to 0.1. Okay, so now delta is completely fixed. It's a constant. It does not change. Okay, and so with delta equal to 0.1, what we're saying is that, what this is saying is that there's going to be some other value, some other constant, unchanging fixed value epsilon that could be equal to what delta is, but it doesn't have to be, but some other constant value epsilon that will satisfy this inequality for any value of x that you could possibly plug in to f of x based on whatever the delta that was picked. So based on delta being 0.1. Okay, but delta and epsilon are variables in the sense that you could start the process over and pick another delta. Say like delta is equal to 5. Okay, and then with that, there's going to be some other value of epsilon that will correspond to the delta being equal to 5. Some other single constant unchanging epsilon value that for all x values that are constrained within an interval given by that delta equal to 5, you take any of those x values, you plug them into this absolute value here, and no matter what, this absolute value is always going to be equal to whatever the epsilon is. And where, again, whatever epsilon is can be anything. It could be equal to 5, but it could be anything. Epsilon is its own separate variable from delta. Okay, and so, but again, what is this inequality here? We talked about what this inequality corresponds to, but what does this correspond to? Okay, this is saying that the absolute distance of the function output from some single finite value L, which is the limit value, what the limit is equal to. And so with the absolute value, this distance is above or below L, doesn't matter. F of x is above or below L, doesn't matter. Just the absolute distance is always less than this epsilon value. No matter what values you plug in from this delta restriction over here. Okay, and now, but you can think about how this inequality here could correspond to whether or not the output is being sandwiched, like it is here with this example for the line 2x minus 1, or just coming from above or just coming from below. Either way, it doesn't matter. Okay, and so now if for a given limit, we can mathematically prove that what's being said here for the precise definition of the limit is true, then how does that prove the limit from the whole infinitely powerful calculator perspective? Well, okay, that's what the textbook is really trying to illustrate on these next couple of pages. So like, okay, first they use this illustration of how a function is a mapping of inputs to outputs. So if we come to the next page, so a function is such that you have inputs x mapping to outputs f of x. Well, okay, if we have some limit to where everything we just talked about and the precise definition of the limit is true, then the idea is you can pick absolutely any value of delta that you want, as long as delta is greater than 0. This could be 0.00000 trillion zeros 1. And what this means is that you're specifying some set of x values around the limit point A that are a distance delta on each side from A, but not including A itself. Then if you would map absolutely all of those x values contained in that interval to the output, then if the limit exists and is equal to L, you're going to find that there is a ceiling on how far those outputs stray from the limit value with that ceiling given by epsilon. Okay, and so the idea then is this. You can view this from either perspective of starting with the input, then going to the output, or vice versa. Like starting with the output, you could specify some epsilon value. You could ask the question. So if I want to be within Planck's constant from some finite single output value L. So Planck's constant is like 6.626 times 10 to the minus 34. All right, now, but one thing to note is that according to this diagram, that this epsilon that's specified is a distance both above and below the limit value. But in general, the specified epsilon doesn't have to sandwich the output from above and below. It could be the case that the epsilon is just a distance on just one side of L, above, just above or just below. Either way, the definition of the limit is the same idea. However, with a two-sided limit, like we're talking about here, it is the case that whatever the specified delta is, that does always correspond to the delta distance both from above and below the limit point. But again, when it comes to the specified epsilon, if that epsilon corresponds to a distance above and below L, or it's just strictly a distance of epsilon above or just strictly below, it's all the same idea as far as the definition of the limit is concerned. Doesn't matter. Okay, but the idea is that based on this epsilon value of Planck's constant, there's going to 100% of the time be some other value delta that corresponds to this Planck's constant epsilon, to where delta represents some ceiling distance of the inputs from both above and below A. Okay, but then again, you could go through this same process starting from the inputs. You specify delta first, and then you would state that there is going to 100% of the time be some corresponding epsilon, and epsilon that corresponds to that delta. And so the key is that because it must be the case that epsilon and delta are absolutely any real numbers in existence that are greater than 0, then you can get however close to the limit value or to the limit point, the input point you want. There's no limit to this whatsoever, how close you can get to L or A. And that's the main idea of why the limit exists. It's because this doesn't all of a sudden break down if epsilon or delta is equal to 0.0000 1,000 zeros 1 or something. No, it never breaks down, no matter how close you get to A or no matter how close you get to L. Now, you might be thinking, well, okay, if I can specify any value of delta or epsilon that I want, and this has to work, well, couldn't I specify something like delta or epsilon is equal to 1,000, some like big interval? What if maybe the process doesn't work in a case like that? Okay, yes, that's true. You're right. But remember, if we come back to the precise definition of the limit, we do have some flexibility in that regard because of the whole idea that we're thinking about f of x on some open interval that contains A, some open interval around A, right? Like, so what's happening away from A really doesn't matter. That's not what the limit is about. And so because of this open interval around A, part of the definition of the limit, what that means is that if you were trying to prove a limit to someone, you have the ability to actually put an upper restriction on delta if you want. For the case of the opening example we did, with the line 2x minus 1, it doesn't matter if you think about it. But if you wanted to, for some other limit proof, you could say, all right, we're on some open interval near A, so let's say we're within 1 unit or 5 units or 10 units of A, above and below A. And with that, then, what you would be saying is, when it comes to the precise definition of the limit, you would be saying that for absolutely any number delta that is greater than 0, but at the same time less than 1 or 5 or 10. There is an epsilon, etc., etc. You see? And what's critically important for the definition of the limit is that from that point, from that upper limit, once you've gone below that upper limit and you can start picking deltas, then these limit inequalities here, the definition of the limit, never break down under any circumstance. From that point, these inequalities can never be invalid under any circumstance. For no matter what delta you choose within that range of below that upper limit and above 0. And that's where the whole part of the intuitive definition of the limit that we talked about at the beginning of this video comes into play. That the part about what does near A mean, how near is near, well, it doesn't matter. The upper limit on delta could be anything. The upper limit on delta could hypothetically be 0.0000 a billion zeros 1. As long as after that upper limit, then all of this kicks in and remains true indefinitely. So you could pick a delta that is 0.000 a trillion zeros 1. So meaning, after the upper limit on delta, which could be like 0.0000 a billion zeros 1, everything kicks in. So then you pick a delta that is 0.0000 a trillion zeros 1. So that's delta. And then with that, it's 100% the case that there's going to be some epsilon that corresponds to that delta. And then you just keep going. You would pick another delta, a smaller delta, a 0.0000 a quintillion zeros 1. And there's going to be an epsilon. As long as there is some upper limit, some open interval around A, where all of this kicks in, and therefore what that would mean is that there is some L value that's being sandwiched or being approached from both sides above and below, then the limit exists and is equal to whatever that L value is. Okay, now next they give another graphical illustration. They're really trying to hammer home how exactly the precise definition of the limit works. Okay, and so this is from a graphical XY axis standpoint. So the graph of the function. All right, so they've drawn in here, you can see the graph of the function, and the inputs are constrained to some symmetrical interval around the limit point A, symmetrical in that it's you're plus or minus some value delta from A around A, but then not including A itself. So we're thinking about the set of all inputs, the set of all X values that are plus or minus delta from A, but not including A itself. And then they put a column here, this column in yellow, to indicate that this set of X values. Okay, now if the limit does exist and is equal to an output value L, an output value of the function L, then that interval of inputs, that entire interval of inputs is going to map to a set of outputs that surrounds the L value, with the width of the output interval given by what's shown here as plus or minus epsilon above and below L. And then they put a horizontal column or a row in blue here to indicate this interval of output values. Okay, but just like with the input interval, we don't think about the limit value L itself being included in this output interval, meaning none of the input X values in the input interval are mapping exactly to L, right? That's kind of confusing because, like, so what is this horizontal dashed line here for L? I think I said that L is an output of the function, but that's not necessarily the case. It might or might not be. I just meant that L is on the output vertical axis here. You've got the outputs on the vertical axis and the inputs on the horizontal axis. Like, okay, so L is the value on the output vertical axis that is being sandwiched or boxed in. And now, but graphically, we can connect the vertical line corresponding to x is equal to a, with the horizontal line corresponding to the f of x being equal to L. And where these lines intersect is the graphical location of the limit point. We're viewing the limit from a graphical standpoint on an XY plot. Now, okay, you might say, well, look, f of a is equal to L, right? In this case, f of a is equal to L. I thought that you just said that the limit value is never included in this output interval in regards to the definition of the limit. Well, it's not, because remember, x is equal to a is not included in the input interval. This point here, L is equal to f of a in this case. Remember, with limits, sometimes it might be the case that the function evaluated at the limit point is equal to the limit value itself. But that's just how it works out in some cases. What the function is doing at the limit point has absolutely nothing whatsoever to do with the definition of the limit. Okay, so, but again, though, what is this graphical intersection point here? The intersection point of the vertical line x is equal to a and the horizontal line corresponding to the output value being boxed in as delta gets smaller and smaller, where these two lines intersect, this intersection point. Well, okay, the idea is as we get closer and closer to a on both sides, coming from both sides, according to the definition of the limit, what we have graphically is a continuous unbroken curve. So it's like, okay, for a limit to exist, according to the definition of the limit, for the limit as x approaches a of this function here, for that to be equal to L, graphically we can interpret this as, let's say we could zoom in on this function infinitely close in the region of the graph that corresponds to x being equal to a. Just incredibly close, astronomically close. If we could do that, then what would we see? If this limit, the limit as x approaches a of this function, is equal to L, and let's think about this for any function. Let's say this was any general function, not this specific function. For any function whatsoever, if the limit as x approaches a of any function is equal to some value L, and then we could zoom in on the graph of that function in the corresponding to the x equal to a region, astronomically close. What would the graph look like in that region? Well, we would see one of two things. We would either see, so let's say again we're zoomed in. Here's the two scenarios. We would either see just an unbroken curve going from left to right all the way across this zoomed in region, and let's say like this is the x is equal to a point, and this would mean that the function does exist at x is equal to a, but then furthermore, f of a is equal to L, right? Which doesn't mean anything as far as the definition of the limit. It's just a coincidence that it happens to be the case. Or we would see something like this. So again, we're assuming the limit exists, then we would see something like this. So you would have, here's x is equal to a. You would have two unbroken curves coming from either side of a. I mean, it could be going in this direction. It doesn't matter. Let's say it's going in this direction. Whatever. Okay, but it's more than just having two unbroken curves, because those two curves are going to almost meet. It's going to be like this. And so almost meet in the sense that if we wanted to complete the full curve, all we would need to do is just add a single point at x is equal to a, just a dot. And now it's an unbroken curve. Right, so this doesn't have to be the case. You could have unbroken curves coming from either side of A, and you get something like this. Right, and in this case, you can't just complete the curve but with a single dot, right? Right, so for the limit to be equal to L, You're going to have two unbroken curves coming from either side. And in this case, we're saying that f of a is not equal to L in this case. And then they almost meet to where all you would need to do to complete the curve is add a single dot. Okay? And the location of that dot is lined up horizontally with L. Okay? So, but now for this scenario where f of a is not equal to L, does this mean that the function doesn't exist at A? Well, no, it might or might not. This just means that f of a is not equal to L, is all. So it could be the case that the function does exist at A, but the function is equal to some value that we can't see in this zoomed in view. Or it could be the case that the function doesn't exist at A at all. That's two reasons why there would be a hole here. But again, really it doesn't matter. As far as the definition of the limit, what the function is doing at the limit point is meaningless. All that matters is the behavior of the function approaching A from either side of A. Okay, and so that's the set of all input values with this vertical column here, yellow column, and then the corresponding set of output values that all of those input values map to on the output axis, which correspond to this horizontal blue column. And then where those two columns intersect is sort of what's boxing in the limit value, L. And the idea is, if this limit does exist, the limit as x approaches A of this function is equal to L, then the idea is you can make delta smaller and smaller and smaller, as small as you want, infinitesimally small, and as you do this, correspondingly at the same time, epsilon is going to be getting smaller and smaller and smaller. So where this overlapping box region is going to continue to shrink around the limit point, as shown here. Delta is getting smaller, and so epsilon is getting smaller, and this box is shrinking around the limit point. And there's no limit whatsoever on how small delta or epsilon can be. You can make either of these values as small as you want. Or in other words, you can box in on the limit value as close as you want. Now, again, this is a little confusing from the perspective that the limit value L doesn't have to be sandwiched from above and below, like it's shown here. For the case of a general two-sided limit, where x is approaching a single finite value A and the limit is equal to a single finite value L, that there's two scenarios for how the output L is quote-unquote surrounded. There's two scenarios for what epsilon represents. Either epsilon is going to represent a symmetric interval above and below L, like shown here, in the exact same way that delta works. That delta has to work. This is a requirement for a general non-one-sided limit with respect to the input. Or it could be the case that the interval is just on one side of L, above or below L. So the interval goes from L and then just epsilon away from L, below L, or from L, epsilon away from L, above L. So I guess that's three different scenarios. But if epsilon is just on one side of L, it's the same idea in regards to if you keep making delta smaller and smaller and smaller, epsilon is just going to be getting smaller and smaller and smaller. And you'll still just be boxing in, closing in on the limit value, L. Right? Again, this is what I was talking about with this limit here. The limit as x approaches 0 of sine of x over x. In this case, there's no mapping of the outputs above the limit value coming from either side of the input point. This is closing in on L strictly from below L. Okay, and so again, for a general two-sided limit that is approaching a single limit value A, and the limit exists and is approaching a single value L, the delta will always, 100% of the time, represent a symmetric interval on both sides of A. But for epsilon, that doesn't have to be the case. Now, you might be thinking, well, wait a minute, doesn't this create some ambiguity? like, okay, the total input interval width is 2 delta, but then the total output interval width could be either 2 epsilon or just 1 epsilon. Don't we need to make the distinction for a specific limit problem? Well, no, the answer to that question is that it doesn't matter either way. It doesn't matter if for some specific limit problem, the output interval is equidistant on both sides of L or just a fixed distance on one side of L. We just call the width of whatever the interval is for any given specific limit epsilon. Because for the precise definition of the limit, for what the precise definition is trying to accomplish in terms of proving the limit exists, in either case, if epsilon is a two-sided epsilon or just a one-sided epsilon, both cases accomplish the same exact purpose. It doesn't matter. Okay, so now what we're going to do in the next video, in the second part of this section, is we're going to work some example problems. Specifically, we want to learn how if we're presented with a limit, like here, for example, the limit as x approaches 3 of 4x minus 5. So we know how to evaluate this limit, right? We know where this 7 is coming from. According to the direct substitution property we learned in the previous section, since the limit function here is a polynomial, we can just plug the limit point 3 into the function. So 4 times 3 is 12 minus 5, and so 7 is what the limit is equal to in this case. So this limit is definitely equal to exactly 7. Okay, but how do we go about officially proving that this limit is equal to 7 according to the precise definition of the limit? That's what we're going to talk about in the next video.